Hello dear students, we will continue our discussion on ion acoustic wave. So, in the last class we have seen how the governing equations change when we do not impose plasma approximation, right. So, we will continue the discussion. So, we have seen that the Poisson equation needs to be considered, which is written like this: epsilon naught phi 1 k square lambda d square plus 1 is E n I 1 lambda d square. So, we called it as C, and we also realized that there is no need to change the continuity equation, it will remain as it is. So, we have dou n I 1 by dou t plus n naught del dot u I 1 is equals to 0. Substituting for n I 1 is equals to n I 1 e to the power of I kx minus omega t, which implies n I 1 dot is equals to n I 1 minus I omega e to the power of I kx minus omega t. Let us say we call this as equation number D. Now, using equation D in this, let us say this is C1 for example. In C1 we have minus I omega n I1 plus n naught I k u I1 is equals to 0, right. So, we have also used del dot u I1 because u I1 is supposed to be this u I1 e to the power of I kx minus omega t. So, dou by dou x of u I1 becomes I k times u I1. Now, what is the meaning of this? Just we have to wonder what is the meaning of this. It means that the perturbation part is oscillating around the mean value like this in a sinusoidal way. But we have an exponential I, right? So, we have variation in a sinusoidal fashion. So, from this n I1 can be written as n I1 is equals to k by omega n naught u I1. Now, we in the earlier class we have derived n E1 is equals to n naught E5 by kVT, and n I1 is derived now to be equal to k by omega n naught u I1. Now, we have this u I1, right. Now, if you look at the equation number C, if we use n I1 into this equation number C, we can write epsilon naught phi 1 times k square lambda d square plus 1 is equals to E times k by omega n naught u I1 lambda d square. Let us say we call this equation as E and this as F. How did we get F? We using equation number E in C. Now, we have u I1, which is unknown. So let us look at the set of equations, all the equations. This is the Poisson equation and this is the continuity equation, and then we have the same equation. Now we need to solve the momentum equation. Let us bring the momentum equation. We can directly use the linearized momentum equation. The terms of the momentum equation will not change. So for instance, we write it as mi ni times dou ui by dou t plus ui dot del times ui is equals to E ne minus del p. Right. So here the advection term can be neglected because of the second order terms involved in it. We can write the linearized version like this: minus I omega mi n naught ui1 equals to minus E n naught ik phi 1 minus gamma I kb ti times ik n I1. Right. So in between these two steps, there are multiple algebra steps. Number one, what is the first step? Number one, the advection term is treated to be 0. Number two, substitute the perturbation. Let's say ui is equals to u naught plus ui1. Right. Then what is it? Del p. So del p term is this one. This entire term that appears here is del p. Gamma n kb t I. And when you within del p, you have to use the perturbation as n or n naught ni is equals to n naught plus ni1. When you do these three steps, you will get this expression. Now the importance of this expression is this is linear directly in terms of the perturbed variables, right? But if you are wondering how I skipped these three steps, you can go back and see the previous lectures. We have done these three steps in ionocaustic wave and we have obtained this relation. The only thing which has changed now is this phi 1 which appears is the change, and ui1 also carries the information about the Poisson equation. Yeah, see here, ui1 carries the information about the Poisson equation. Poisson equation, why is Poisson equation in this picture? Because we have treated number of electrons and ions to be different. Right. So this equation actually, you see this continuity equation carries the information of both actually, the Poisson equation and the continuity. Now when we substitute, we can use this ui1 from this equation number E into this. Let's say we call this equation as G. Let's not make the lecture notes clumsy, so we will remove all these things, because if you go back and see the lecture notes, it should be easy for you to understand. Okay. Right. Now we have equation number G. Now let us look at the equation number G. What is it that we are trying to do? We have phi 1, right? We have ni1, we have ui1. Anything else which is a perturbed part which needs to be eliminated? No. We have only phi 1, ni1, and we have this and this. So ultimately, when we derive the dispersion relation, it will be in terms of omega and k and temperature Kb, etc. But it cannot be in terms of these perturbed variables, right? Now we have to eliminate this. Now using something that we have just derived, we can write as ui1 is equals to epsilon naught phi 1 k square lambda d square plus 1 divided by E times k by omega n naught lambda d square. Where did we get this? From here. From equation F. Just try to follow the mathematics. The underlying physics will be explained at the end. Okay. Just try to understand how we are combining equations and trying to get the dispersion relation. What is the method? The method is the linear perturbation theory, right? So from F we can write ui1 as this, right? So let us substitute for ui1. Let's say we call this as equation number I. Using equation number I in G, we will write minus I omega mi right. We have just substituted ui1 wherever it was appearing, where, here and here. So we can cancel some things. N naught can be cancelled. N naught can be cancelled. K by omega can be cancelled. And we can cancel this minus, minus, minus. Now we can rewrite this expression as this minus I omega minus I omega mi n naught times epsilon naught phi 1 k square lambda d square plus 1 divided by E times k by omega n naught lambda d square is equals to E n naught I k phi 1 minus plus gamma I kb ti times I k phi 1 to k square lambda d square plus 1 divided by E lambda d square. Right, we can cancel this iota. You can cancel this n naught which appears, and we can cancel phi 1. And now multiplying with multiply the entire expression with E lambda d square divided by epsilon naught E1 times k square lambda d square plus 1. Multiplying the entire expression, what we will get is omega mi times omega by k. You see this, all these things will get cancelled. Omega by k is equals to E n naught k times E lambda d square divided by epsilon naught E1 times k square lambda d square plus 1 plus gamma I kb ti k. Rearranging the terms, and using the fact that lambda d square is epsilon naught kb te by n naught e square, where in this equation we can write omega square by k square mi is equals to e square n naught kb te lambda d square divided by epsilon naught kb te times k square lambda d square plus 1 plus gamma I kb te. I have multiplied both numerator and denominator with kb te in the first term on the right hand side. So if you go back, what do you see here? You have all this k square e lambda d square times. So here we wrote something by mistake. So this E1 is not there. Right. Since phi 1 has already been cancelled, it should be E lambda d square by epsilon naught. So we are actually multiplying with this factor. That's it. This one. Okay. So here kbte is multiplied onto numerator and denominator just to get that lambda d square. So omega square by k square mi is still there on the left hand side. Omega square, omega times omega square by k. You take one k from here and bring it to the left hand side. You have omega square by k square times mi is equal to, so all this e square n naught by epsilon naught kbte. This is nothing but lambda d square, right? So this is kbte by lambda d square times lambda d square by k square lambda d square plus 1 plus gamma I kb t I. So this gets cancelled. So omega square by k square is equals to kb t by mi times 1 by k square lambda d square plus 1 plus gamma I kb ti divided by mi, or omega by k is under root kb te by mi into 1 by k square lambda d square plus 1 plus gamma I kb ti by mi. So, this is nothing but the dispersion relation, omega versus k. Right. Now, let us compare this expression with the earlier expression. What is it? Omega by k is square root of kbte, let us say gamma e kbte by m plus gamma I kbti by m. Now, the relation, this is when plasma approximation is valid, and in the absence of that, omega by k is slightly different, which is kbte by mi times 1 by k square lambda d square plus 1 plus gamma I kbti by mi. Right. So, this is the difference. So, expression looks similar because we have gamma I kbti by mi appearing on both sides. Except for the additional factor. What is the additional factor? The additional factor is 1 by k square lambda d square plus 1 is the additional factor. Why is this additional factor when plasma approximation is of course valid here, not valid here? This is the additional factor which has come into existence just by treating the number of ions not equal to the number of electrons. Right. Now, this is the additional factor. The error, the order of error can be the order of error. How much is it changing with respect to the actual value is order of error is k square by lambda d square. So, we can simply say that the error introduced is because of not following the plasma approximation. So, we know generally that lambda d is very small when we consider plasma. So, we can say that lambda d, since lambda d is very small, the order of error is also going to be very, very small for long wavelength waves. Further, we can also say that when the temperature of ion tends to 0, we can simply write lambda d square is equal to 0, right. So, at shorter wavelengths k, which is 2 pi by lambda, for shorter wavelengths k square lambda d square will become much greater than for small lambda. K square lambda d square becomes much larger than 1 and or very large k. For small value of lambda, k becomes very large, or we can say that omega square will become equal to k square. When we plot this, let us say omega versus k, it will look something like this. This is k and this is omega. and this is omega p. So, when k square lambda d square becomes very large, or for very small waves, omega by k, which is the phase velocity, can be written as kb Te by mi times 1 by 1 plus k square lambda d square plus gamma I kb Ti by mi. When k square lambda d square becomes very large, or when lambda is very small, we can say that this term becomes very small and can be neglected. Right. When for very small values of lambda, what happens? K becomes very large because it is 2 pi by lambda, and 1 plus k square by lambda square taken in inverse becomes very small. So, for very small wavelengths, this factor can be neglected altogether. So, this is the difference when we compare the ion acoustic wave in the presence of plasma approximation and in the absence of plasma approximation. Right. So, we will conclude this discussion here.